Introduction to Mathematical Proofs playlist. Today we'll be talking about the principle of mathematical induction, or induction for short. That's what everyone else calls it. So you're like, why is this useful? And I'm like, let's think about a ladder. Imagine a ladder with infinitely many steps, labeled from 1 to, I guess it never ends, right? In order to climb the ladder, okay, show me that you can climb the ladder like infinitely as long to whatever step you want. You'd be like, okay, let me try to get to the first step. So you're like, okay, uh, well, yeah, nice. We got to the first step. Then we have to go to the next step. Okay, so we go from 1 to 2. Okay, then we go to the next step from 2 to 3. Okay, then we go to the next step, 3 to 4. And you can keep repeating this process over and over and over. But we need to ensure that this works for every number. So from step like 21 to 22, or like 32 million to 32 million and 1. So the idea is you need to show two things. One, that you can start at the beginning position. In this case, is going to be the number 1. And two, secondly, you can go from any step to the next step. So if k is a natural number, you can go from step k to the step k plus 1. Mathematically, if we think about like the closed forms that we were talking about last episode, you want to show the formula holds for the step k plus 1, knowing that the formula holds for step k. So hey, if we're able to get to step k, can we get to the next step? Maybe you don't like the ladder, maybe you like the staircase. But me personally, I like Benny the frog. Okay, so this dot right here, ribbit, ribbit, he goes ribbit, ribbit, because he's a frog. His name is Benny. Benny's a dot. And the idea is Benny needs to jump on every single lily pad numbered from 1 to, well, I guess it never ends. So imagine that after the 5, there's a 6, 1, whatever. Benny starts on lily pad 1. So that's the first thing to do. Then he hops and hops and hops and hops. And you need to show that every single time that hop is valid, or Benny can go to the next one. So these are two different ways you like to think about it. I'll stick with a frog example. Now the question is, what does this have to do with math? Let's say we want to show a closed form or find a formula for like a summation or a recursive formula where we rely on the previous part. We have to claim that the formula works for every single number. So with Benny helps, we'll show that this formula, 1 plus 2 all the way to plus n, is n multiplied by n plus 1 all divided by 2. That's what we'll show. And there's actually a small caveat that I want you to notice here. We'll use n when we're talking about the formula itself and not actually k. We'll only use k when we're actually talking about a specific number. So 1 plus 2 plus, let's say all the way to 10, we'd use k is equal to 10 for that example. But the formula itself, we're going to use n. So let's prove this formula with Benny's help via the principle of mathematical induction. So the first thing we have to show is that our formula does work for the very first number. This is the same as showing that Benny can indeed reach the first lily pad. This is what we like to call our base case. So let's just confirm this. The left-hand side, or the summation, is just going to be 1, because 1 plus, well, you're not adding anything else, it's just 1. While if we use k is equal to 1, the right-hand side, or the formula, becomes 1 multiplied by 1 plus 1, which is 1 times 2 over 2, which is 1. So indeed, both sides are the same. So the formula holds for k is equal to 1. So our first lily pad, or our first step, or our base case holds. Like the first foundational thing is true. Now we'll go prove the second thing, that Benny can go from one lily pad to the next lily pad. So we have to show that Benny can go from lily pad k to lily pad k plus 1. The assumption that Benny can reach lily pad k, or that random lily pad that we chose, is called our induction hypothesis. When we think about this in our closed form or our formula, what we're assuming is that the formula holds for some k in the naturals. Then we want to show that it holds for k plus 1. Remember what's happening here? If Benny can reach lily pad k, or the formula holds for lily pad k, then, this is an implication, then the formula also holds for k plus 1, or Benny can reach lily pad k plus 1. Remember our diagram? 1, then 2, then 3, and so on. You can't actually show, hey, Benny can jump from 1 to 2, then 2 to 3, then 3 to 4, then 4 to 5, because there's infinitely many of these numbers. So you have to show this for any arbitrary natural number. So the most general form. Kind of like how we talk about even numbers, we can't show a property for every single even number, 2, 4, 8, 6, 10, and so on. We have to choose the most basic or general form that'll cover every single even number. So that's the form 2k. Right? But in this case, this is just going to be any natural number. Now we're going to show that our formula or claim works for k plus 1 using our induction hypothesis. This is called the inductive step. Let's think about what we want to show. We want to show that 1 plus 2 plus all the way to plus k plus 1 is the same as k plus 1 multiplied by k plus 2 over 2. It's crucial to understand that this is what we're trying to achieve. Original formula is k times k plus 1 over 2, but we want to show that it holds for k plus 1. So then when you add 1 to each k, it becomes k plus 1 multiplied by k plus 2. And that's what's happening here. That's what we want to show. So now let's actually solve the left-hand side and see what it equals. And we're going to use our induction hypothesis this time. So we're going to substitute 1 plus 2 plus all the way to k with the fraction k times k plus 1 over 2. But we'll keep the plus k plus 1 that's on the right side by itself. The crucial thing in the inductive step is that we use our induction hypothesis. Otherwise, it doesn't really matter what lily pad we're on. So now all we really need to do from this point on, now that we have everything set up really nicely, is some simple algebra so that the steps are clear. So when we expand this out using our induction hypothesis, we get k times k plus 1 over 2 plus k plus 1. And then we expand everything out, we get k squared plus k plus 2k plus 2 all over 2. And then if we factor that out, we get k plus 1 times k plus 2 over 2. And that's exactly what we want to show. So we've shown that the formula does hold for k plus 1, assuming that it holds for some arbitrary k. So we showed that Benny can jump from lily pad k to lily pad k plus 1. And this is actually all we need to do. Since we've shown that our formula holds for k plus 1, assuming that it holds for arbitrary k, since we're combining this with our base case, it must hold for every number. Because remember, our base case is 1, then we can go from any random k to k plus 1. So you can go from 1 to 1 plus 1, which is 2, then 2 to 2 plus 1, which is 3, then 3 to 3 plus 1, which is 4. And this will hold for every single number. Every single jump is viable, so every lily pad is reached, which means the formula holds for every natural number. So the formula, 1 plus 2, all the way to plus n, is equal to n times n plus 1 over 2. And we did all of this purely algebraically. Remember how last time we did let's pair this number up with that number, or think of the triangle. We don't need to do all of that. It's just straight up algebra, which is really, really nice. And you can expand it even further. So let's just do one more example to get used to this. 1 squared plus 2 squared all the way to plus n squared is equal to n times n plus 1 times 2n plus 1, and this time all divided by 6. The question is, okay, where did I find this? Where did this formula just come from? It just kind of appeared out of nowhere. And that's kind of the beauty of induction. You don't need to know where the formula came from. You just know that it is. And maybe there is some intuition, but the intuition behind this formula is way, way harder to understand than just adding up the regular terms. You might need to go into 3 dimensions, for example. Actually, that's exactly what you need to do. And you're like, oh man, oh my gosh, right? That's tough. But what's really interesting is that you can keep expanding this. So there is a formula for 1 cubed plus 2 cubed all the way to plus n cubed. And all you need to use is induction to prove it, as long as you're given the formula. Okay, now let's actually start our proof, our induction proof. So we start with our base case, the first lily pad. So the left-hand side, our sum is 1, because 1 squared is just 1. While the right-hand side is 1 multiplied by 2 multiplied by 3, all divided by 6, which is actually 6 over 6, which is 1. So we're good. Now we go on to the inductive step. So let's first take a look at what our inductive hypothesis is. We're going to assume that our formula works for some natural number k, and we want to show that it holds for k plus 1. So in frog terms, Benny can reach lily pad k, so that Benny can also reach lily pad k plus 1. So then this is the same as wanting to show that 1 squared plus 2 squared all the way to plus k squared plus k plus 1 all squared is, and remember what we did last time, the original formula is k times k plus 1 times 2k plus 1, but then we add 1 to every single one, since we want to show it holds for k plus 1. So this is k plus 1 times k plus 2 times 2k plus 3 all over 6. So what's really important is we set up our scope. Okay, this is what we want to show. Let's proceed with the inductive step. So we have the following. So we have 1 squared plus 2 squared all the way to plus k squared plus k plus 1 all squared. Well, let's use our induction hypothesis and turn that left-hand side, 1 squared all the way to plus k squared, to k times k plus 1 times 2k plus 1 all over 6. And then we're going to start expanding everything out and then collect like terms. And then at the end we get 2k cubed plus 9k squared plus 13k plus 6 all over 6. There's lots of algebra happening. And while that's somewhat important, since you have to understand, oh, hey, where's the mistake? Why are things not lining up? And indeed, I also had like a small algebra mistake over here. It's just algebra, right? Algebra is grade 10 stuff. All that's really important is to understand why this is true. The process and the methodology is more important than the actual step itself. Okay, so now we got to this end form right here, and like, okay, how does this help us? How are we going to factor this out? It gets really confusing. So another thing we can do is, hey, why don't we expand out what our right-hand side is supposed to be? So it's supposed to be k plus 1 times k plus 2 times 2k plus 3. What does that actually expand to? It also expands to the same thing, 2k cubed plus 9k squared plus 13k plus 6 all over 6. So indeed, both sides are the exact same thing. So since the left-hand side and the right-hand side are equal, the inductive step is complete. Since if our formula holds for k and then it holds for k plus 1, it means that Benny can jump across every lily pad, so it holds for every natural number. And honestly, that's all you need to write. When you're done with the inductive step, you say that the inductive step is complete, so our claim holds for every single number. You don't actually have to explain the, oh, because of this, because it's already implied. But I'm explaining this because this is your first time understanding what induction is, going through the concepts, and to make sure that the understanding is solid. Remember, the methodology is more important than the algebra of what's happening. Remember, if this doesn't make sense, just go back and think about Benny the frog. So here's the final tip. Whenever you're doing an induction proof, you always need to use your induction hypothesis. This is the thing that we assume for our arbitrary number is the fact that Benny can reach the lily pad K. We'll need this somewhere because we need to know where we are to jump to the next one, to the next step. And if you don't ever need to use your induction hypothesis, then it's either that, like, you know, you're going to get stuck somewhere or kind of went overkill because you actually don't need to use induction at all. You could just prove it directly. You might be thinking, okay, induction's a very limited tool. Why would this ever be useful? But as you'll see in the next video, trust me, induction, you can generalize it and it becomes pretty useful in many other things. And that ends it for now. So I'll see you in the next video with Benny's friend.